so they should help you since you need some sort of accommodation. And then I'm just trying to double check that it's on Blackboard, the link. Does anybody remember? Did I post a link on Blackboard?
I haven't checked.
That's fine. I'm pulling out my Blackboard, it's just slow. Yeah, it's under the announcements. If you go to the Blackboard page under the announcements, then it has a YouTube channel, and you should be able to find it from there. All right, awesome. If you need any more help, just text your friend.
Thank you.
Thanks.
Hey, yeah, so I'll check in with you in labs coming up and coordinate with the professor, and we'll try and figure it out. Hey, you're super welcome. Good morning. Hey, and I wanted to check too, it's completely my own fault. I left things for last minute because I'm really good at day craving. I had yesterday open, but I also get migraines. I hadn't had one in a while. I had one yesterday. So just getting through my lab was a thing, but I'm late with my organism journal. I'll be doing it anyway. I don't know if I should email it or just bring it Tuesday.
Yeah, just bring it Tuesday. It's
Okay.
fine.
Yeah,
Yeah, don't worry about it.
Any deduction or lack of credit is super understandable because I don't have it.
Yeah, it's okay. Yeah, you can come in. All right, everyone's struggling today.
I'm in the correct class then. Oh, no. I should have.
Yes, please. Sorry. I'm like managing here. Oh, sorry. Yes. All right, sorry for the late start. We have a couple, actually, accommodations with the elevator, childcare issues, apparently. So hopefully people will be joining live, and they should be streamed. So for people in the chat, I'll just say please chat once they get on. Hopefully they're working on that. All right, so I actually wanted to talk about something because I don't even think he's here today, and I'm sorry I don't know your names yet. I'll try to learn them in lab today as I pass back papers. But somebody had asked, is there a fan in the Gulf of Mexico? And yeah, was that your question? Oh, okay, I'm sorry. See, that's how terrible with faces I am sometimes. But yeah, so you apparently asked, is there a fan? And I felt bad because I didn't really give you an answer. I was like, yeah, it probably looks like there might be, but I wanted to actually give you a real answer. And if you want, I could post this paper for fun. It's talking about, actually all about the turbine system, so you could get an idea what a research paper in this sort of thing would look like, people in the field. And it's always good to at least kind of skim through the papers. I always encourage you, get in touch with the primary sources. Never let anyone on the media or the internet tell you how to interpret a paper. You got to look at the paper yourself, read the conclusion, and authors will put their conclusion at the end usually. So even if you don't know how to read a scientific paper, start with the abstract, start with the conclusion, try to look at the pictures. That's always a good way to look at it. Just go slow. It's better to at least just kind of see what you can interpret. And so the main thing that I wanted you to take away from this is just looking at the Mississippi fan. And so just orienting ourselves, the Mississippi River runs somewhere around here that it would be dumping out. And it is kind of fascinating because the fan and the deposits are so far away from shore here. And I think the paper made some note that the other reason why they deposit so far was because you have the continental shelf here. So remember, we just at least talked about, right, continental shelves. And so now we can kind of see, oh, here in a paper, this is how they describe it. And they see that because of this continental shelf there, that the deposits from the Mississippi River are actually all the way out here, creating that Mississippi fan. And I think they comment like how large the fan is. And apparently there's other features, like smaller fans, and admittedly I don't know the origins of the Bryant fan. Then there's also just other features that they point out, like this large escarpment, which is just a long slope. So again, just gives you a taste of the field. So I can post that then online if people are interested.
Oh, that'd be neat. I grew up in North Central Florida, so I'm in love with the Gulf.
Ah, okay, so that's,
Gulf Stream and all that.
yeah, I actually grew up in Houston, so I'm somewhat familiar with the Gulf, but not really from a geological perspective.
Same boat, I just like to swim.
All right, so now we're looking at chapter 4, and it ties in really well with today's lab, which should be fun, I think. So just a general overview. So we'll look at marine sediment both today in lab and today in lecture. And I'm going to say winner, winner, chicken dinner. If anyone can find evidence of like fossils or shells in their sand samples that we'll look at today. I can't promise that you'll find any, but we'll be looking. So just let me know if you find anything really cool. And of course, we'll kind of go through the chapter. Look at the marine sediments, and then of course many resources that these sediments provide. And so just a broad definition of a sediment, that's just going to be some eroded particle from a larger piece of rock or land feature. And so that's just fragments of dust, dirt, or shells, little bits of fossils, anything. And so then eventually we have these suspensions settling, so those small particles, make their way further out deep into the ocean and settle down. And of course, we want to try to look at the layers of deposit and see what clues, maybe what organisms are there, try to figure out any sort of ocean circulation patterns of currents, how do things get deposited, and that's probably what the paper goes into a lot if you were to read it. And then any other sort of big global events. And so we'll get a taste of this in lab, so we'll look at how kind of to characterize it, so we'll sift it, and then just kind of look at how you classify it by their shape. And again, we'll try to see what's in there. So there's, of course, lots of minerals. You'll basically learn that the Earth is just silicon dioxide and a bunch of calcium carbonate, though it seems like. I think we kind of mentioned that in our previous chapters, we hinted. So it's just kind of repeated in these sediments. And probably a lot of the rock samples you'll look at as well will be like quartz. So a lot of rock everywhere is just quartz. So that's just silicon dioxide, and it's colored with little impurities. And so sediments can, of course, pack back down and make sedimentary rock. So this chart is at least a good overview of just kind of everything in this chapter. So you can see it's a summary of everything that we're going to go over. But we can look at this chart later. All right, so what were kind of the challenges to, of course, studying the earth floor, and what were some early techniques? What are some modern techniques? What do you remember? What do we know?
Sounding.
So that was used to map the ocean floor, but now we're trying to physically get samples. And so the question, yeah, so rope in a bucket, that was the earliest way, right? Simple method, just try to get.
Yeah, the sounding lines, they used to keep a
So excellent. So buckets or dredges is the term they have there. And of course, right, that's not the greatest. You also kind of disturb the sediment, so then you can't really study how they layered on there. So of course, more modern exploration, now they focus on trying to get just a core sample, and of course, working a lot with the oil industry to actually perform those tests. So, yeah, any of you have experience on that, or? I was curious. Yeah, so of course, right, all those deep sea rigs are looking for oil, but they can also be mining for samples as they, test the soil as well. And so that's really cool. And so of course, lots of collaboration too. Again, this type of research requires a lot of collaboration with a lot of big partners. So you have those Scripps over in San Diego with a lot of these efforts, of course, sponsored by the NSF for research and other institutions for oceanic studies. And so they also work together in this deep sea drilling projects. I think that was one of the first efforts to try to do core samples and not just kind of dredging. And so this is where they started getting at least some evidence of the ocean age, again saying how much younger the ocean floor is than our continental land. So again, lots of collaboration efforts. And so paleoceanography is again just a study of how the ocean, atmosphere, land interactions have produced changes in ocean chemistry, circulation, biology, and climate. And so of course this is just an example of a core sampling. So of course, right, they're very careful to preserve the layers. And this is where you try to figure out, what's the rate at which all these things were deposited and try to compare, what is the different composition of these, what clues does that tell us about, the chemistry of the ocean or the organisms that were there at the time. And then, of course, try to compare it to other deposits and get a sense of currents and how things move in the ocean. Again, obviously very difficult research. And so you can look at the sand and different sediment particles and describe them by their origin. So a lot of sediments, especially the ones we've been talking about with the fans, those are all going to be lithogenous. So just like we were talking about with the Mississippi fans, so that's going to be all the sediments, right, that the Mississippi River is bringing down, any erosion that's happened, so that's going to get deposited. And then biogenous, this is going to be derived from organisms, so diatoms or any calcium carbonate organisms. Hydrogenous is just going to be anything that comes out of solution, essentially. And all this means, right, there's so many ions floating around, carbonates, phosphates, silicates, irons, random metals, and so just, again, depending on the chemistry, we'll get a sense everything's in equilibrium, everything is just one giant chemical reaction, back and forth equilibrium. So sometimes if you just have the right conditions, that could cause something to precipitate out, and we'll kind of look at that more in detail. And then cosmogeneous would just mean something is derived from outer space. So a meteor hitting, right, that's cosmogeneous in origin then. And so we just use the term lithogenous, but another alternate term that you might see is terro or terragenous, so terrain, that gives you a sense of land. And so this reflects the composition of rock, of course, from where it's derived. And again, that's a tricky part of research, is trying to understand the origin of these particles and then how far they travel. So that's something that they look at. How far can particles travel by wind, by water? And so, of course, all this is produced by weathering. And so what are different forms of weathering? How can things erode? Just give me some. So rain, of course, wind, that's an excellent one. Waves. Snow's a good one. Earthquakes. Tsunamis. All these are good. I'll put ice and snow together because those are good. Yeah, that's a really big one with the ice and snow cracking. Yeah, I think those are the big ones. You guys got it. So, right, all these weathering processes that occur every day. So, of course, right, our landscape is always changing from weathering. And so, again, we can try to track how far are those small particles transported. Wasn't it like a couple of years ago you had the Sahara winds or whatever, where like the particles from the Sahara Desert were coming all the way to North America? So it's all that, right? They're trying to track wind patterns, how far everything can travel. Probably, yeah, yeah. So that's all part of what they study, exactly, because that's how everything kind of transports, and yeah, minerals being transported around. It's really fascinating. Yeah, you guys got it all. And so like we've been seeing and studying, and now we saw in a paper, so there's the greatest quantity around those continental margins. So of course, right, you have the continental margins, and then after that, where it starts dropping off, that's where a lot of these sediments start getting deposited. And like we learned in the last chapter, that's where you see a lot of those fan formations and those sediments, right, spread out. So that's why they make those big flat areas. And so like I was saying, you'll probably discover everything is mainly quartz. And so we'll be looking at this today under the microscope, examining these particles. And you'll probably see a lot of clear, shiny looking pieces, and it's probably just silicon dioxide. Yeah, here's something. So this was listing in 2000, tracking a windstorm of dust from the Sahara. But I feel like I remember that's a occurrence that occurs. Again, just fascinating to see that, see how the minerals are exchanged. And let's see, this is just quartz concentration. So just kind of tracking maybe where they're deposited. You can kind of see that in these maps there. And so of course, the size of the sediment indicates how far it will be transported. And we have this Wentworth scale of grain size. And so we have our particles, so we can have, of course, boulder. That's going to be anything above 256 millimeters. And so, of course, that's going to be coarse. And this will not travel too far out, so that's going to be deposited right near the stream bed, near the source of the river, or maybe along some beaches. But it's not going to get really far out into the middle of the ocean. And so we see, as we go further and further out to these finer particles, right, they tend to get further and further out as well where they're deposited. So, right, cobble, pebble, granule, and again, you'll get a real physical sense for this in lab today. And then you have your beach sand, so that's going to be, deposited where the beach is to kind of your continental shelf more, and then your silt, so all that finer sand, right, that starts getting deposited further and further out. And so all it's saying, right, with this high energy, low energy, obviously the boulder is going to take more energy, so then it's in comparison at a lot higher energy. So thinking about the current of the river, so it's going to be deposited more high energy versus the silt and the clay, which they have there is low energy, so meaning like out in the middle of the ocean where there is not a lot of movement. That's when it's going to start settling out more. Yeah, that's another way to look at it. And of course, that's proportional to size. Excellent. So, yeah, larger particles closer to the shore. And this is just a way to describe, the composition of the sediments in that area. So are they all well sorted? Are they the same particle size? Or are they really varied? So that can tell you something about the forces going on. And so we can also classify it by where it's found. So neretic, do people remember what this term means? Or is it found, if it's neretic origin? You can kind of maybe look at the first.
Near.
Near land, so the coast, yes, so it's coast. Oops, I can't. What am I doing today? Coast, so yeah, origin being in the coast, it's going to be neretic. So of course, if it's the coast, it's going to be close to land. Then the deposits there, of course, will be mainly lithogenous, so again, from the earth or from the land. And that makes sense. So right, all the larger deposits, again, coming in from the rivers, eroding the lands, that's going to be deposited near the coast. And then pelagic, what do we think this term means, sediment origin? You can kind of guess. Well, yeah, deeper waters or ocean, right? Ocean. So sediment that we find then in the ocean, or the pelagic sediment, then, so this would of course be found in the deeper water. And again, you're going to find those finer grains, and they're going to be deposited kind of slowly as they might drop out of solution. And so we have different classifications of our then coastal rock deposits. So we can have our beach deposits. So these are mainly wave deposited quartz-rich sands. Again, everything's quartz, kind of the theme of this chapter. And then we have our continental shelf deposits, and then our turbidite deposits, so more from our turbidity currents, and then any glacial deposits. So this could also be looking at old deposits, and we have to think about too how the sea level has changed. So we speculate, right, that first we were covered at an ice age for a while, and then now that it's melted, so our sea levels have risen, and so that's also caused different patterns of deposition. And again, so now we're starting to kind of get a theme here. So now again, our deep ocean sediments. So we know they're going to be fine grain. We know they go out slowly. And so again, evidence what you're looking for, maybe if there was a large enough volcanic event, if there are a lot of volcanic events, what can we see deposited? What kind of dust? Again, how far does that dust come from? And what's being deposited? Where are those currents? So that helps us see the flow of the deep sea currents.
In the situation where you're talking about the volcanic ash, that's not from underwater volcanoes, that's from regular volcanoes, right?
Yeah, although it technically could be both, but, right, because you're interested in both, because you could see a big volcanic ash, right, so the ash spreads around, and then eventually it conglomerates with water, gets deposited. So yeah, how far can you see that effect? But yeah, if you had an underwater volcano, there was maybe like a really, really large, like crazy deposit, that could be another clue. So it's all, yeah, you got the right idea. You got to be open to everything, because you don't know where those deposits are coming from. And that's where you can compare, because we said, the volcanoes can have different composition of materials and chemicals, right, with those metal sulfides, different ratios. So you can compare, right, that ash composition to what does it look like, where might have been the origin of whatever ash we're studying. So obviously, right, a lot of variables, but you guys are kind of seeing it. It's awesome. And then, of course, the other type of, again, oceanic sediment we'll find will be clay. And so you have 70% of your clay-sized particles come from our continents, obviously very fine particles. And then red clays are going to be, of course, iron rich. And so you can look for that just anytime you're trying to look for clues as would happen, do you have iron rich deposits or not? So now let's look at biogenous sediment. So what does biogenous mean? Life. So from life. And so then this is the hard remains of the once living organisms, so their shell. And so you can have macroscopic, and so you've probably seen that before, shells on the beach, maybe you found bones or shark teeth. And then eventually, right, all these things can be crushed down and turn into tiny microscopic shells, or they end up making that ooze, which I assume, was that the ooze they were referring to in that first lab, where they said throw the rock down and check for the ooze? Yeah, I didn't understand it at the time. But now I'm starting to see. So yeah, that biogenic ooze. And so it's mainly algae and protozoans. And we have two main chemical components. So again, there's our silicon dioxide, and then our other chemical of the day, calcium carbonate. So we mentioned in previous lectures, it was kind of our big buffer in the ocean, but again, it's everywhere. So both just naturally occurring in large mineral deposits, but also being exuded by living organisms. And so we have these diatoms, and so they're little photosynthetic algae. They, of course, provide a lot of oxygen. And then they form diatomaceous earth. And so what's diatomaceous earth? Who's familiar with it? How does it work? What does it do? Yeah, that's what I was looking for. So it's used to kill bugs. At least that's one. And it's very natural, safe. So the book talks about all its other uses. So for example, it's used a lot in chemistry, or even just like, I think it mentioned winemaking, other product refinement. So it's really good at just a filtration. So I actually use sea light a lot in my chemical profession. But yes, it's used to kill bugs. So how does it work to kill the bugs?
The soft bodied, it's like little silica spikes.
Yeah.
Around in fiberglass, so it goes in between their body segments and makes them miserable and/or punctures and lets them bleed out.
Yeah, exactly. So it like physically rips them apart. So it's pretty crazy. I mean, just the scale of it in my mind is mind blowing. Where you have this tiny thing, and if you were to feel sea light in your hand, it's really soft feeling to us, but on a bug scale.
Like broken glass.
Yeah. Yeah, since like you could eat it and it won't hurt you. And I don't recommend eating it, but it doesn't really do anything. It might be like have you heard of people like eating charcoal as a purification thing?
I do that because I have gluten allergy, so if I come in contact with it, I have to have charcoal and stuff like that. It's weird.
Yeah.
And it really helps.
Yeah, but there's like two tails to that. So you have to be a little careful with the charcoal because it can also just leach out, anything in general. So obviously you're using it for something specific, so that's awesome that it works for you. But I've heard some people, like it's a trend, especially like in LA, they were making those black ice cream cones with the black waffle and the black ice creams all with charcoal, and then some people are getting sick. So that was why, a little too much of the
Yeah.
You have to be careful because if you take vitamins or medication,
Right.
you can take that out also.
Yeah, exactly. So it's always a balance, right? If you're trying to detox, then take the charcoal, but don't overdo it, because yeah, you're taking out your good minerals if you're trying to put that in.
I wanted to ask, like chemically, 'cause I know you use like carbon filters for like removing smells and everything. How does the carbon bond and attract things for this removal?
It's just more like a physical capsule
thing?
thing, like it just physically
porous.
packs it, yeah, and it just like kind of attracts it. Yeah, it's kind of weird, like I'm not sure it's, sometimes it seems like magic when we do it in chemistry. Like I've done it, you know, you boil it something with carbon and then it does actually make it a little purer and whiter, so it's kind of weird, but. Yeah, and like I said, the book mentions they use it in industry a lot. Like it's a very common inert filtration thing that we use all the time. All right, so then shifting from so this is more, again, our silicon dioxide with our diatoms. So they're all silica based. And so these organisms produce calcium carbonate then, the coccolithopores. And so these are photosynthetic algae. And then they have these plates, which they are named coccoliths or coccoliths. I'm not sure how to pronounce it. I'll have to ask Google later. But basically, right, these little individual plates, once the organism dies, those plates become the little sediments of calcium carbonate. And so you can, again, just have large deposits of calcium carbonate occurring naturally or from some large deposits. So this is the White Cliffs of southern England. So, of course, this would be used potentially for chalk or whatever you need calcium carbonate for. And then this other species, so this is a protozoa, this Foraminifera here, and so it makes little shells. So these shells are called tests, and so this is just a picture of it here, and basically they resemble little mini seashells, and then they produce, again, calcium carbonate from these shells, so they're all calcium carbonate, these. And so then we can look at how, sorry, my laptop's not charging, how these organisms are distributed. There it goes. And so that kind of depends, and we'll look at this, I think, in the visual later. So productivity, so basically how many organisms are there, so that alludes to the concentration. And then, of course, destruction, so depending on if there's skeletal remains, do those dissolve and degrade, what's the rate of that? And then, of course, we can have dilution, so do we have other sediments coming on top and then diluting our biogenous sediment deposits. And so again, looking at these ooze, so it tells us kind of where organisms are. And so it's kind of like a chemistry thing. So thinking back to, have people made like rock candy before? Yeah, so the idea with that, right, you get a super saturated solution. So you take a sugar, boil it with water, probably add some cool food coloring. So you get it hot, super saturated, and then you cool it down, right, and then it makes the beautiful rock crystals. And so the similar concept is here, right? It's all just dissolving solution chemistry. And so what they're saying, if you have an area that has a small amount of organisms, and of course, right, life cycle of organisms, living, dying. But if you just have less of it, you're going to have less silica sinking. So, right, the silica test just refers to their shells. And so, of course, if it's in solution and there's not a lot of it, it's just not going to drop out of solution, like the rock candy case where there's a lot. And so the area of high productivity where you might see the ooze then, that means that you have to have more silica in solution around that local area. So then higher concentration means that that's going to lead to some eventually dropping out as solution. And of course, if you have more dropping out, then it will continue to kind of build. And then hopefully you can see those deposits preserved later as well. So does that make sense? It's just saying that, right, with the ooze, it tells us that there's a lot of organisms in there. And the reason why we get the ooze deposited, though, is because there's lots of organisms. So I use the rock candy analogy, right? So you have a lot of sugar then in one solution. So in that area, you have a lot of organisms. And so just like the sugar comes out of solution if there's too much in there, same thing, you'll start to get those deposits in that area.
Basically a history of the organisms that live together.
Yeah, so exactly. So if you have that preserved, you get the history of those organisms in that area. Excellent.
It would, sort of like when you go in rivers and, like more large scale, how you get the slippy rocks, because things like to kind of grow on
Yeah.
the silicon quartz and bits. So in areas with lots of organisms, you'll get a higher deposition on the particles themselves. They'll also increase their weight, so they'll fall and accumulate.
Yeah. It's the same thing, everything just accumulating, yeah. So yeah, once you start getting deposits, it slowly gets a little more favorable. Yeah. Kind of, again, if we go back to the coral reef concept, right? You need a nice area for things to come out of solution, a little less currents. That's why they formed in those lagoon areas. So same sort of concepts there. And so again, back to these neuretic deposits, so of the coast. And so we can, of course, also have carbonates found there. And so we might see some fossil shells, so I'm sure you've seen that at the beach. And ancient marine carbonates constitute about 25% of all rocks. And of course, we hope to open rock samples and find things inside to study. And so we can have carbonate deposits. And so this is kind of cool, this stromatolite from the cyanobacteria. And of course, it layered and it layered over time. I mean, just like you're saying with the rocks and, organisms depositing the same thing. So this was a favorable conditions for this cyanobacteria. So over time, it just continued living and layering. And then, so what's also interesting is in our modern day, a lot of large deposits of calcium carbonate occur around the coral reefs. So that's kind of fascinating. And so again, going back to the coral reefs, our nice shallow place for things to deposit.
Isn't the coral made out of calcium carbonate? Because I just went to Hawaii and they were talking about the parrotfish and how it eats the algae or something off of the coral, but sometimes it gets bites of the coral and it recycles it and comes out as sand.
Let's see. Yeah, so they are mainly made out of calcium carbonate.
And a lot of the sand on the shore there is thanks to the parrotfish.
Yeah. So it's all a cycle, and so right, it needs calcium carbonate, so it makes sense that there's lots of deposits of there, and yeah, that's awesome. And so there's current stromatolites are apparently located in Australia, so I'm sure they're potentially making more of these there. And so this is, again, just ooze, but now calcium carbonate-based ooze. Again, same concept about the rate of supply versus kind of the rate of when shells dissolve. So, of course, warm, shallow water can be saturated with calcium carbonate, so warm. Also, general basic concept. So if you have a warm water, it tends to dissolve solids better. But then gases are the exception. So gases are opposites. So usually we think we heat things up and things dissolve better. But gases go down actually in warm water. And maybe put another note, so gases have opposite solubility than solids. And again, this is just in general, so there are a few solids that actually decrease solubility as you increase temperatures. But again, for the most part, warm things dissolve your solids better, but then warm things are poorer at dissolving gases. So important. And so this means our cool, deep ocean is undersaturated with calcium carbonate. But what's interesting, and I think this comes up more in our next chapter if I remember correctly, but this also means our deep ocean is going to be more saturated with CO2. So, right, if it's poorer at holding our sediments, but then gases and solids have opposite solubility, that deep ocean is going to be a reservoir of CO2. So everything's a cycle, everything's in motion.
So when you say the gases go down, does that literally mean sink?
That's supposed to be of lower solubility. So actually, I guess we should say gases bubble and rise out of warm things, right? And you could imagine the difference. If you have a warm soda and pop it open, it'll go flat really quickly. And that's just because, right, that gas, it's hot, it's going to escape, especially as soon as you pop that pressure. Then a cold soda will keep that CO2 dissolved longer.
Yeah, doesn't cooler water also hold more oxygen saturation? So is it just all gases, colder water?
Yeah, so all gases are going to be greater at deeper ocean, yeah. And that's also the compressibility, so gases, can compress more too under the pressures of the ocean, so you start getting that factor. And so, blah, blah. So this is slightly repetitive of what we saw, but now we're just seeing it right with the calcium carbonate case. So same thing, just like we saw before, if there's going to be a lot of deposition, then we have to have phytoplankton. And so just showing distribution too of your calcite. And so again, below this calcite compensation depth, high CO2, and if you have high CO2, we'll learn how that makes it more acidic. And then obviously, this is how we got the evidence, like we mentioned, for our seafloor spreading and our continental drifts. So they took samples of the seafloor as well. And again, we saw the changes in magnetism through this. So we can see our deposits, how they move out, so all that. And so this is also just interesting, showing the calcium carbonate content. Let me zoom in just a hair. And so a lot of the larger calcium carbonate deposits seem to come along these fault lines. But they're also out in the deep ocean too, so it makes sense that it would settle out in the deep ocean. So kind of showing similar information. And so other minerals that we can have, that you can get these manganese nodules, which are pretty cool, blue-looking things. And then, of course, there's lots of phosphates, carbonates, and again, we mentioned those metal sulfides from the volcanoes as well. And so again, you can have things precipitating out, just depending as well. So there's a lot of factors. So we mentioned with the still ocean, that can cause things to precipitate out as well, especially if you happen to have a higher concentration, again, for whatever reason, depending on the local chemistry. And so these manganese nodules are pretty cool. And so, again, these might have fossils inside, giving some clue of how they formed. So in their formation, they'll pick up fossils. So here's another nodule, again showing how if you cut it open, you can see layers of its formation. And so phosphates are important, and of course we want to use the resources of the ocean, as people generally tend to do. And so a big use for phosphates is in fertilizer. And again, those metal sulfides, so mentioned associated with hydrothermal events. Oh, and then these evaporites. So halite, this is sodium chloride. So of course, we might want to get minerals that form so when your seawater evaporates completely, then it can leave behind different minerals. So of course, table salt. What's gypsum used for? Yeah, drywall. That was a big one I was looking for. It's probably good for soil. Like everything's always good to like remineralize your soil. That's always like a good part of gardening because your plants are taking out all those nutrients. So yeah, you always got to replenish. But yeah, excellent. So drywall. So big need for gypsum. So of course there's always gypsum mining for the drywall. You're fine. And so of course you could also try to look for evidence of space dust. How is that distributed? And then just kind of overall. And right, this makes sense. So by definition, we said Noretic is obviously just around the coast. So that's only going to be about 1/4 of the seafloor versus our pelagic deep sea sediments. So that makes sense that would dominate the majority of the seafloor. And so again, just kind of a cute map. So you can see patterns of how things are deposited. So you can see the clay, right, way out in the ocean, the really fine pieces. You can look at where the diatoms are, so calcareous ooze, so ooze everywhere, especially with land. And then, of course, all the near shore follows all the coastline. And so, of course, distribution, like we're seeing, it depends where that source is. So back to the paper, right, they're studying very specifically the Mississippi River and really studying how far out into the Gulf do all those deposits go from the Mississippi. So that's interesting, right, how far out into the ocean. And then, of course, again, you can tell how productive and how abundant your microscopic marine organisms are. And of course, right, you want signs of microscopic marine organisms because that also usually means there's larger life organisms. You can examine the history. And then, of course, we mentioned, right, the depth of the water. And then any other seafloor features, right, mountains underwater could influence currents. So all those things, trying to understand the currents better. And this is just another graph comparing the types of deep ocean sediment and where they are found. But for the most part, they're pretty similar. If you notice, right, the North Pacific Ocean seems to have proportionally a lot more clay. And that probably makes sense since it's a lot bigger, so it has just a lot more open area to have a lot of deposits compared to like the Atlantic, the Indian here. And so these microscopic tests are all the little shells from the organisms slowly sink to the seafloor. And of course, this could be a long process. And some of these biogenic tests clump together as fecal pellets. And so things will accumulate, and again, you could try to study everything you can. And then just more, again, sediment thickness. And so again, greatest thickness closer to the shores, we're gonna have a lot of deposits. This is actually kind of interesting because we're, again, talking about this area, so that's pretty thick in sediment deposits in the Gulf. And again, challenges with this, obviously, even with our modern technology, it's still difficult to even like mine resources from the ocean. I'm sure that'd be something people would want to do. And so there is, of course, a lot of petroleum out there, so they mentioned that as well in the book. So all those diatoms, all those microscopic organisms, their bodies as well eventually become petroleum. And so 30% of the world's oil comes from offshore resources. And again, it takes a lot of resources to do offshore drilling. Then these gas hydrides are pretty cool. So what they are, these clathrates, are basically frozen water, but water that's been like defrozen so that they have little pockets of gas, so mainly methane. And it's pretty cool. Basically, you know, you set them on fire. So kind of cool. And a few people are worried that, you know, if they suddenly all melted, you get a lot of methane release, but methane gets an overblown bad rep. And so again, just more, this is again, who knows? They're just saying if all these things collapse because they're little spheres with little gas, and you might have some sort of slope failure, and like features and shelves may crumble and get a tsunami hazard. But, you know, who really knows what any of that will look like. And these gas hydrates do have a lot of usable energy, but probably difficult to actually harvest and use. There has been a lot of research to try to like trap hydrogen and different small molecules in different inorganic structures, probably somewhat mimicking this, but not much true progress has been made. Okay. Again, our evaporative deposits, phosphorus. This is just cool looking at the manganese distribution. Again, looking a lot of it is in the Pacific, so probably pretty difficult to mine. And of course, right, we're always interested in our rare earth elements with our cell phones, trying to exploit somebody to mine. All right, questions about this chapter? And I will post notes today. I am behind on notes. I just was in meetings all day yesterday. So I owe you notes. All right, let's see how far we get into chapter 5. So chapter 5 now goes into a lot of chemistry.
It's your favorite chapter then, right?
Oh, I'm excited. I just hope everybody else is. So, what are some of the beautiful things about water?
What provides energy?
So, life. What about its basic properties? Now we're thinking thermal. What about it?
It takes so many forms.
So it takes a lot of forms. And it is fascinating, right, that we can see it in its solid, liquid, gas phase all on Earth. What else can we say about water? hydrates us. Yeah, so it's a good, oh, I think solvent. Yeah, I knew where you were going there. So excellent, and that's a really big one. Like it is like everything is literally dissolved in water, right? We just spent the whole last chapter talking about our huge ocean and everything is dropping in and out of solution with the ocean. So yeah, it's a beautiful, beautiful, beautiful solvent. And we'll look at why it's such a good solvent. So basically because it's polar. Well, yeah, because it's polar, yeah. And so I think you're referring to that it does cohesion where it can kind of stick to, yeah, and that's just because it can hydrogen bond, which we'll talk about. So I wouldn't use the term break, but dissolve, yeah. So you're just disrupting the intermolecular forces between them because ions, right, don't have physical bonds, they're just electrostatic potential charges. But yeah, you got the right idea, and we'll look at that, how water, it has, because it's polar, has a negative side, a positive side, and so then for our sodium chloride, all right, the sodium will be kind of attracted to that, and the water would all circle it around. And so same thing for the chloride, except it'd be surrounded by hydrogens. And we'll look at that in this chapter. So we're just kind of touching on everything. What else? People haven't said the one magic word that I'm looking for with the thermal. So it regulates temperature, and then what do we mean by that? Yeah, and then do you know why? What property gives rise to that? Why it can regulate the ocean?
Back to sort of the convection thing, the density.
It's just a certain
Level of
property
molecular
of
activity.
it. Like if you compare, I'll just so it's specific heat, or it's I think it's specific heat. So basically, how much energy does it take to change the temperature? And so think of it compared to like a metal, right? You touch metal, it feels really cold to you, and that's because it doesn't take a lot of energy to heat up metal. So metal has a pretty low specific heat, and we'll look at that. But yeah, because it has high specific heat capacity, then it can kind of regulate our temperatures. That's why the coast and West Coast is the best coast, but we're regulated by the ocean, kind of kept nice and cool. You know, the Gulf is a hotter ocean, so that has less of a cooling effect. We have the nice Pacific Stream here, so we're very spoiled on the West Coast. And yeah, again, we've been touching on this, so salinity, temperature, density, all that. You know, we've been talking about density, the difficulties with exploration, so all that is from water. All right. So, of course, the presence of water on Earth makes life possible, and we won't go down the rabbit hole of why Earth has a bunch of water versus other planets. Philosophical or geological discussion for another time.
Frozen water also special because it floats compared to other frozen substances?
Yeah, and we'll talk about that. So that's super unusual, and so that's also works well for the Earth, right? The glaciers get a float on top, but then you still have organisms that can live on the bottom. And so, yeah, we like water. Organisms are mainly water. We have a lot of water to keep the chemistry even just going in our bodies. And so we'll look at the chemical structure of water. And so just general chemistry. So they try to cover like everything of chemistry at once in this chapter, but we'll try to take hopefully an easy overview. So atoms are just the building blocks of all matter. So if you forget what an atom is, right, just turn and look at the periodic table though. So all those are atoms, so our basic building blocks. And hopefully you are aware from other science classes that they are made up of protons, neutrons, and electrons. So the main concept being that these are in the center, called the nucleus. And then the electrons float around in orbitals, but we won't get into that. That's what gets me really excited, but most people are really bored. And so this might be another key concept that we want to take away from this chemistry chapter, is the number of protons distinguishes the chemical element. And all that literally means is if you walk over to the periodic table and they have a number here, so number 1 is hydrogen, and that means it has 1 proton. And it just continues on, 1, 2, 3, they go in order, not too hard. You know, you have carbon, 6, so it has a big number 6, you know, it has 6 protons. So that's a basic thing we should take away, hopefully. So then molecule is just 2 or more atoms held together by shared electrons, and they should be different. So different atoms. And not to confuse people, but so for example, are you aware that like nitrogen is found as a diatomic, like the nitrogen you breathe, or oxygen? So this is maybe getting into too much chemistry, but the point with a molecule is it has to be different. So even though there's 2 of them, this is how they exist in their elemental form, so meaning they're found in nature like this, so this would be called a diatomic. There's other forms of elements, not to go down the rabbit hole again, but like a diamond, for example, is only carbon, so that would be an element, not a molecule. Sulfur is sometimes shown like this, S8, and just naturally it makes this little 8-ring structure. Yeah, still elements, so that's kind of an aside. All right, so molecules, again, we said they had to be different. And they want you to know that there is a covalent bond between oxygen and hydrogen sharing electrons. Is this too much chemistry? Or is... If it's not on the test and I'm just like explaining to you how those shared bonds form, is that okay?
Yep.
Okay, so all I'm showing here is oxygen has 6 valence electrons, and I drew that. And so that's often another characteristic of water is you have these 2 lone pairs, and that's also why oxygen is negative on that side, so they just kind of oversimplified it. And then it has these 2 lone electrons, which are prime for bonding. Hydrogen brings 1 electron as well, and so that's how you get that shared bond. So each one is contributing 1 electron. But again, all you need to know is that's covalent. And so again, they're physically sharing, and this is, I'll put a slight note, so different from ionic. So again, ionic, there's actually a transfer of electrons. Now I might just get too excited. I'll try to restrain myself. So there's a transfer where you make charged ions. And so there's no physical sharing there, hence why they can be dissolved versus our water. So that kind of makes sense. I'm not trying to throw all this in the exam, just trying to at least show what's going on. All right, and then because I drew it like this, because I get too excited, this is why it has a bent shape. So it has this degree of 104.9 degrees, and so that is a little bit of force there from the lone pairs pushing down on the hydrogens, bringing them a little bit closer together. So those lone pairs occupy a lot of space. But you do want to know that, so know that water is bent. I at least ask that. Please don't draw it as something linear. I might cry. I think they use the wrong word here. They combine two terms. So they want to say polar and that it has a dipole moment. But you don't need to know this term. This is too much. Just know that it's polar. Oh, I think they meant two poles. I don't know what they meant. Two poles, question mark? What do you mean? Okay. So what happens when you have non-chemists try to explain chemistry. And so polarity just means that we have a negative charge at the oxygen. So again, probably want to know this. This is key. And this is, right, the explanation, the detailed explanation. But maybe you just kind of remember, oh yeah, oxygen tends to be pretty electronegative. Maybe you've learned that trend before. And then hydrogen tends to be pretty positive. And actually what makes hydrogen bonding so special and actually unique and really powerful, and we really need to appreciate how powerful, because there's not enough emphasis. And so what's interesting is, right, hydrogen is so small, it's teeny tiny, and then it only has one electron. And so of course not only does oxygen have a bunch of lone pairs on it, but oxygen is what we call extremely electronegative. And so that just means that it wants those electrons. And so poor hydrogen is already sharing that electron, but then oxygen's like, nah, I really want it closer to me. And so that really gives us this positive end at the hydrogen, but that really strong force, the fact that hydrogen is almost stripped of its electron, is what gives you hydrogen bonding.
Oxygen being much larger than hydrogen also plays a big role in that, right? Or no?
Size in this case doesn't matter. But yeah, even though hydrogen is teeny tiny, but I mean, you could say that's why it gets stripped, but the fact that oxygen is larger is not. And so other things, and this is an aside, so you don't need to know this, but you can have hydrogen bonding in other scenarios, like if you have hydrogen and nitrogen, and hydrogen and fluorine. Those are also, so if you look at the periodic table, do a quick tour. So fluorine is the most electronegative element, so it really wants those electrons. And then oxygen and nitrogen are right next to it. So if you have hydrogen bonded to any of those three, then you can have a hydrogen bonding scenario. But then the hydrogen bonding itself, and this could get kind of confusing, the hydrogen bonding itself is an intermolecular force. And so let's break that down. What it's saying is it's this bond between the molecules. So what? And let's just recap. So what we're saying, so we said oxygen, and I'll just kind of highlight it in pink here to show electron density. So right, oxygen's basically carrying all that electron density. It already had lone pairs, and then it's really pulling everything towards it. So hydrogen's feeling pretty positive. But then notice in the orientation that because it's so positive, that oxygen from another water molecule is going to be kind of attracted to it on this end. So it's going to be, I need my ball popper. I wonder if you can do that to students. I shouldn't make fun of it because I was a student that fell asleep in class. So I've had professors like throw stuff at me, like throw stuff. I don't know, you want to give him a gentle shake? I know, water. We should be excited. You're drinking it. It's fascinating. It's beautiful. All right, welcome back. So this is where we have that hydrogen bond then. So this, I just want to be really clear. And the only reason why I'm being so explicit too is because I've seen organic chemistry students missay stuff and use wrong terminology and say we're like breaking bonds too when we're boiling. It's like we're not breaking any bonds on the molecule, we're breaking the intermolecular forces. So no water molecules got exploded, right? When we turn them into steam, they're just higher and higher in energy and moving faster. So that's just a really important distinction that I wanted to make. And so yeah, you mentioned that they stick together and have high cohesion. And did you ever do that in elementary school where you try to put so many drops on a penny, and then maybe you do it with like alcohol too? And so the point is, right, water has a high surface tension, so it's super polar, so that means it just sticks to itself as well. And so that's why on the penny, and so that's my crappy penny. So you can tell I'm not going to be judging your pictures. They already look way better than anything I could ever draw in my life. And then you get the large bubble of water versus any organic. A better example would be, let's try heptane. Hexane is more widely used, but hexane is actually toxic. You probably shouldn't use hexane. That's my safety tip of the day. Don't breathe. I know that somebody out there is using too much hexane to clean up an oil spill. So anyways, you use a hydrocarbon there, and you won't get a very good bubble, and it'll probably just like puddle out. And if you get really bored, you could probably convince me to bust some pennies out and do this. And so like y'all have mentioned, it has a high solubility of compounds, especially those ionic compounds, since those are charged, and that's how they get actually physically dissolved. And then again, we have the high specific heat, so we're getting that. And then it uses the term unusual density. I would just say beautiful density. That'd be my term. So 1 gram per centimeter cubed. That's such a nice, oh, that's supposed to be a happy face. Okay, that's embarrassing now. Try that again. And so this is what I was trying to poorly draw earlier. So again, going back to, you recognize that salts dissolve in there, and this is why. So all the negative chlorine anion in this case would be oriented towards our positive hydrogens. And then our sodium would be nucleated by the oxygen negative end. And so that's how things dissolve. And so y'all also mentioned the states of matter. And you also touched on how important snow/ice is for breaking things. So that's a big physical mechanism, right? Water seeps in. And then you also mentioned water is less dense, so then it occupies more volume as a solid. And so this is kind of the picture why, and this is fascinating. And so usually as things cool, right, they get cool, more dense and packed tighter. But water does this thing where it arranges itself by all kind of the hydrogen bonds. So notice, right, it's very oriented very nicely. So it organizes itself into this pattern, and that pattern takes up more space. So of course, I'm sure you've seen that if you accidentally put a bottle of water in the freezer. If you're just trying to do a rapid cool tool, everybody's done that mistake, right? And then you come back, your bottle's shattered, whoops.
Or when people put soda in the freezer, it just explodes.
Yeah, that's always a sad day. It's sadder if you like forget about it too.
Yeah.
And so of course we call that process freezing. If you go from liquid to solid, melting. If you go from solid to liquid. Yeah, and then molecules move freely then in the liquid state, so this is just liquid form. And now it occupies less space than the ice since they're kind of more free to move and move around, so they're not locked into that geometric pattern. And as we go from ice to vapor, you just want to know you're increasing in energy, but that should be instinctual, right? That makes sense. And you see that a lot when you take the water to the gas. You know, you have to put it on the stove and heat it, and then you wait forever. And then you want to know these terms, so vaporization, and you're probably familiar with this from liquid going to gas, or you could also call it, right, evaporation, boiling. Those are also appropriate terms. And then condensation, so we see that obviously rain coming back down. We could also have deposition. So deposition is a more specific term of gas going to solid. So that could be snow, or sometimes gas just freezes at high enough altitudes down in deposits. And then we could also have sublimation. So same thing, you can have a solid piece of ice then, but then some of it is in equilibrium with the atmosphere and slowly subliming and becoming gas. And not sure what your book was intending to go for, but I didn't want to go down too far the rabbit hole. So van der Waals forces are basically everything has a van der Waals force. And this is what we want to get from this. So everything has van der Waals. And so let's try to figure out what they're trying to say in some senses. So let's compare, let's compare methane versus water in the boiling points. And let's just look this up. And well, we know water. So what's the boiling point of water? So 100 degrees Celsius. And then if anyone wants to race me, I'm looking up the boiling point of methane. Preferably in Celsius. Okay, I got it. So methane is negative 162 degrees Celsius. So I think the main point that we want to understand from this is, so literally everything has van der Waals forces. So every little atom, and all that's is from the small change in momentum of the electron moving around. So like you have two atoms, let's just say they're helium for simplicity's sake. So helium's just by itself. Then it has those two electrons moving around. And so there's a temporary dipole. So let's say the electrons are to one side. And so that's going to create attraction between them. And so that's a van der Waals force. So again, all we need to know is that everything has them, but they are the weakest interactions. And you can see that in the difference here in their boiling points. And so since these forces are so weak, again, they're intermolecular forces. So if we're looking at methane, and so why I picked methane is simply because it has hydrogens on it, just like water, except methane is what we would call both nonpolar, because it just has hydrogens around it. And hydrogen is not very electronegative. It's also evenly distributed. So it's completely nonpolar, which means it only has van der Waals forces. But now this is showing you really the power of our hydrogen bonding. Because look at that crazy difference. Like, that's incredible when you think about it. And that is super low, negative 162. So we're not going to see methane as a solid normally. But water, it's so high, even though it has such a small molecular weight, it's such a small molecule. Like, just appreciate that. Like, it really blows my mind as a chemist, like, thinking about that. Like, it is such a tiny molecule, but those hydrogen bonding forces are so strong that it has a boiling point of 100 degrees Celsius. Like, hopefully that blows your mind. And, okay, I'll just put as an aside, you can also have polar forces, but we're not going to go there. So there's actually like 3 types of intermolecular forces of van der Waals, polar, and hydrogen bonding. But we just need to appreciate really the power of hydrogen bonding. Yeah.
Yeah, so the van der Waal forces versus ionic bonding, are they a part of ionic bonding, or is that like when you're just shy of ionic bonding, when you're kind of influencing each other, or how?
Ionic bonding is actually stronger than like hydrogen bonding. So looking at then those forces of solubilizing, like, so what we were just talking about, sodium chloride and water, that bond is actually even stronger. So that's is a slightly different force. So it's not usually grouped as part of the intermolecular. It's usually a little separately. But yeah, that's really strong, the ion dipole forces.
Covalent stronger or weaker than an ionic bond?
Sorry, one more time.
Covalent bond?
Covalent bond is stronger than an ionic. Yeah, and you can think about it, right? They're physically sharing electrons in. All right, so heat is just transfer of both kinetic and potential energy from one object to the other. So again, just transfer of energy. And then we use the temperature to at least give us the average kinetic energy of molecules. And calorie is the amount of water needed to raise the temperature of 1 gram of water by 1 degree Celsius. The only problem with this is not a food calorie. Do you know what a food calorie is equal to with this calorie? This is more just trivia. So it's 1,000 calories is called a kcal, or just your regular calorie for your food calorie then that you see on the label. So that's a lot of energy. You can, start to think about your energy in food and then translating that. It's all mind-boggling. And so again, here they're just showing, at least trying to emphasize, although this was, in my opinion, a poor graphic, because I don't know what the similar compound is, but again, all they're showing is the power of the hydrogen bond. And then, so heat capacity was the term that I was looking for, or specific heat. And so they're one of those terms. So heat capacity is just formally defined as the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. And so, again, what we want to take away from this is that water has a high specific heat capacity. And, sorry, I'm just scrolling around. You can see different units on this. Like usually you see the heat capacity is 4.18. I think it's joules per gram as well for the heat capacity of water. Just double check that number, yeah. And so just be aware you might see heat capacity in different units. So in this unit that's shown here, it's given in calories per gram per degree Celsius. And again, what we're appreciating is that metals have a lot lower heat capacity. So mercury's down there, copper, iron, and of course oil is a little bit higher. And then
Is that the temperature by which it boils or melts?
so this is the amount of heat that's required to raise 1 gram of that substance by a degree. So it's different from melting, but again, just think about how, like, right, you can touch this metal and it feels cold, right? But then if you touch like a piece of wood, it maybe doesn't feel as cold. You touch this, doesn't feel cold. You touch water, probably would feel fine. But it's just right, the metal has a low specific heat, so right away that energy transfers and it's taking it and it's quick with it, versus water where it takes a lot more energy. Like you could try even heating up, if you put a hot iron on the stove versus the same mass of water, the water is going to take longer to heat up versus the metal. So, does that make sense?
Sorry, this is like all new stuff for me, so.
No, ask questions. So it's different from melting point. So melting point is just when those intermolecular forces separate. And of course, metals they're a lot different in just how those materials come together. So it just requires them to reach a much higher temperature to get melt and movement. But then actually raising it to that degree requires less energy per gram.
Just how fast it takes energy.
Yeah. So that's another way to put it.
Sort of say how easily is it excited? Sort of equatable.
Excited makes me think of electrons, so that would not be what I'm going for. Yeah, excited and electrons, that's more like fireworks and the result from that sort of explosive reaction. So that's like a lot more heat, a lot quicker, because there you're exciting electrons to get pretty colors. So yeah, this is just, and maybe that makes sense, and this is kind of maybe hopefully not too gruesome to think about, but just like a branding iron, right? You get it hot really quick, then it's hot, then you quickly brand the animal, but it's only a small localized burn in some senses because it has a low relative heat. So like, yes, you get it really hot and yes, you burn, but then it only does so much because it only has so much energy per gram is what we're getting at. Versus that amount of water, water can actually be pretty dangerous, right? If you get water boiled on yourself, like that was that poor woman who got coffee in her with McDonald's, like obviously the lawsuit's another story, but just the point of the damage that water can do because it has such a high specific heat. Like boiling water in the face is really dangerous, like, or steam, yeah.
So can this work in reverse as well? So like it heats up really quickly, but then it cools down really quickly as well?
Yeah, exactly. So then water takes a long time to both heat up and cool down. So going back to the temperature regulation of the earth, right? That's why we're not fluctuating. It's because our water acts as a sink to kind of regulate that. You have a comment?
Yeah, we use this concept a lot in life because we want to determine, for a pan, what can heat up quickly, or a pot holder, what can resist the heat.
Exactly, yeah, same sort of ideas. So, all those metals, right, they heat up quickly. Some of that relates to conductivity, so they're somewhat related, but not. But yeah, exactly, same sort of ideas, picking the right materials. Yeah, or thinking about, like fancy cooking techniques where they like heat up the iron or the slab of rock. Usually they do a rock slab, I think it is, or maybe it's quartz or granite. Does anybody know what I'm talking about? Where like you heat up the stone and then you have the fancy steak and it just like delicately cooks on the stone, and that's supposed to be special. So all that's right, heat capacity, yeah. But it's all ultimately heat capacity and how that material transfers heat back and forth.
Like if you're using a metal pan to bake something in compared to a glass pan, the plastic can stay hot longer.
Yeah, exactly. So I forget which one you're supposed to use if you want your cake to be fluffy. But yeah, right, that's the exact right idea. It's like, depending on what you're baking, if I had better baking skills, I would know. But yeah, you'd want to pick the appropriate material too.
Baking would be a chemist's dream, I would think.
Yeah, it is totally chemistry.
Not my thing.
Cooking, you don't like cooking? And so it also uses this term latent heat, but that's again similar sort of idea where it has this heat capacity. Sorry, overexcited scrolling. And so this is just an energy diagram. So all it's showing here is, let me zoom out just a hair. So right, this is energy increasing there in the unit of calories. And right, this makes sense. So just think about, I took some ice out of the freezer, maybe you left it out on the counter. And so notice, right, you're adding energy then it's changing temperature. And what you should note here is anytime you're looking at this energy diagram for any substance, you can see these flat plateaus here. And anytime you have a flat plateau, that indicates a state change. So that's pretty cool. And what that is also telling us is we're still going to be at 0. So we're not changing from 0 until we take all our ice that started at point A, as indicated here, and then we turn it into 0-degree water at point B. So that's all that's showing. And then, of course, keep adding heat. Take it to our next phase of matter, so liquid to water. And then again, there's your state change. And this is where I was saying even steam can be even more dangerous, right? You want to be careful. So steam starts at 100, and then of course you can keep adding energy. And so it gets transformed. So now we go from liquid to gas. And also appreciate, so notice the difference, right? So they say it has a high latent energy. And so what's that telling you? Well, it's a lot more energy to be in the gas state for water versus the liquid state. So that steam has even more energy, so that could be kind of dangerous. And then, of course, right, you can keep heating that steam. So now this is all steam, gas, phase, and, it just goes on to theory. But that's a basic thing. So I'm trying to think what I would want to ask is like maybe label a point and you say like the state of matter. So if it's down here, it's ice. If I label this point, there's a state change. Something like that. Does that seem relatively? Yeah. Yeah, like if I show parts of a graph or like if something is here, you can identify it's water vapor. And I'd probably label, so I wouldn't have it labeled as so, but I might label, boiling point or something. Try to help it. So trying to think of questions for an exam, yeah.
So, state changes, you say there's a plateau, so during a state change, is it somewhat in both states? And then when it's kind of climbing again, it's completely in that state, like the state change between ice and liquid water, across that calorie increase where the line is at that point, that's where it's a little bit of both. And then from B to C is when its only state is as a liquid. And then from C to D, it would be somewhat liquid, somewhat vapor, and after D, solely vapor.
Yeah, exactly. Yeah. So let's see. So I'm not going to ask you any questions like I do with my other classes. So usually I make people calculate how much energy it takes. You could appreciate that you can do that. So for any substance, you can look up, right, heat of vaporization. You can look up, so you end up having to look up a lot of things, but basically you can do it because you got to look at specific heat. So how much energy can it take in its solid, liquid, and gas phase? And then you have to calculate, of course, how much energy it takes to heat up that specific amount of material, again, depending on its heat of melting and heat of vaporization. Blah, blah, blah. Let's see. And of course, right, condensation and freezing are just the opposite processes. So opposite. Boiling. And so the idea is it requires the same amount of energy. So just like y'all were saying, right, it's the same energy to heat up. So if it's slow to heat up, it's slow to cool down. So same thing, right? It's the same amount of energy that it had to gain. Now it has to lose to go back to the liquid phase or the ice phase. So same thing, opposite of melting. And then this is just another molecular picture, again emphasizing the 3D structure of water, that it's less dense. Then we have water, and then of course in the gas state, all of them are floating around and very far apart, so minimal intermolecular forces there. And so now starts to explain, obviously, things we see on Earth. So I'm sure you guys are aware, right? Our oceans don't boil, and we don't have a bunch of frozen solid polar oceans. And so all those heating and cooling kind of creates ocean currents, and so we can kind of see the general movement here of water. So we have in the warmer places, you have these evaporation latitudes. So obviously where water is going to be evaporated, goes into the atmosphere as a gas form, and then as it is carried towards the poles, obviously it starts losing energy as the poles are a little bit colder, and then we get more precipitation in the form of rain or snow. Since it's all moving as a current, so everything is always in motion. Right, yeah. So you never have one spot that just like gets energy pounded, right? It's going to get hot and then it's going to evaporate, move on.
So just basically the very top part gets warm enough to evaporate, but it's not.
Exactly, yeah.
Are there also places in the ocean where there's almost like a wall of water being separated by like the different temperatures? Like I've seen different things where it almost looks like two different types of like water.
Yeah, there's probably like weird current action from that, because it'd be cool if you brought like the specific example, but yeah, like depending if you have like hot currents meeting colder currents, you can get weird like action.
Like when you have like a river going into a lake, a warm body lake, yeah, you'll see the difference
Yeah,
right there at those points.
exactly.
And thermoclimes, like back to the Gulf of Mexico, where that continental shelf comes, and you go from the shallows to the deeper water, you get a really strong thermocline.
Oh, nice.
Yeah, with clear water on the one side, and then it goes from that light blue to the dark blue, both with the depth and the level of sunlight.
Yeah.
Similar things off of England, where the Gulf comes towards the end by Cornwall. My mom's English, so
Oh, nice. That's cool. And so again, like we've been saying, our oceans moderate the temperature. And so the biggest thing we can see in this effect is this chart here. So let's just orient ourselves. So we have red being much hotter, kind of this bluish is no day to night change. And then there are a few areas which are apparently cooler during the day, at least when the sample was taken. And so looking at that, we see obviously the middle part of the continents tend to have a lot of temperature changes. So large temperature changes, that makes sense. And we think about too with the desert, especially if there's no clouds, no water to help keep the heat in, right? You get those extreme fluctuations with the desert where it gets super hot, baked by the sun goes away, now it's cold. So
Is the ocean constantly just like replenishing itself like through that evaporation process?
yeah, and then, you can that's part of how, water gets purified and ends up as fresh water too eventually, right? The ocean water can become rain, those salts that obviously make the ocean water impossible to drink when we're on the ocean, right? Then it gets evaporated though, salts get left behind, and if it rains down, in lakes and rivers or, snow, like we got a lot of snow this year, so we have all that snow pack deposit, which is coming down. And we can think about, right, the eroding all that snow had been causing just even locally. Does that answer?
And the rivers just feed back into the ocean.
Yeah, exactly. So everything's always one big solvent water globe. And so density is just defined as mass divided by volume. And I feel like they made this overcomplicated with this picture. Well, we really just want to appreciate, so water basically just has a density of 1. They're trying to show minor fluctuations here and, showing how the ice forms and the density changes, but, they make it look really drastic with this chart, but, obviously the density will slightly fluctuate, so as the waters increase, slightly lower, but all we really need to take away is water has a density of 1. It is useful. It is also a great property. It's used in separating, as a practicing chemist. That's why you can separate things so you have your nice product. And ideally, your organic compound goes into your organic layer, like ether or something else. And then your water is there. And so you can separate it. You can purify things. So density is great. Also probably, again, the sea life can live in water. It has just a density of 1, so it's not weird to swim in. Like even with those super salty oceans, how they can be really buoyant, right? That could be maybe more difficult, but with our ocean, it's just 1. So we have snowflakes. So snowflakes would then kind of mirror. So you have to think about your seat of the crystal and the hexagonal shape of our ice, right? So our ice structure. So that's kind of how the snowflakes grow. Again, thinking of the rock candy analogy again is kind of appropriate for this same thing. A crystal seeding, any sort of crystal growth is just similar sort of concept. It's just things nucleating on and growing. And yep, we've all done this before. So pop our can. And blah, blah, blah. So just basically adding stuff to it, right, changes the density. Dissolved solids also reduce the freezing point, which is kind of important. So this is also helps salt water not freeze. And the same concept is used when we put salting the roads. Although I would say, right, salt is probably not the best. I notice around here locally they tend to use gravel, rock. So that's probably a lot better, especially when we're thinking about our freshwater streams. So there's some concern that, places that use a lot of salt, eventually that's going to end up into our freshwater, and then we're contaminating our fresh water with salt, so that's.
They use a red clay on that Klamath
Yeah.
40 route. They use a red clay for that reason.
Yeah, so I think that's cool.
It's crushed lava rock stuff on the east side.
So yeah, that's probably a way better alternative. So clay, lava rock,
And sand.
sand. So all that. Yeah, and that's true too. Enriching the soil, you guys are awesome. Tying everything back together. We're all, again, one big chemistry reaction here. And so, of course, we can quantify the ocean by its salinity. So that just means, usually we're looking at dissolved solids as in dissolved ionic compounds. And you could also, of course, get a gas analysis as well. And so usually salinity is expressed in parts per 1,000 here. So that's just 1/1000 is what that means. And so typical ocean salinity is 35 parts per 1,000. So right, 34 and 1,000. So all that's saying is 35 sodium chloride molecules for every 1,000 water molecules, essentially. And so again, this just kind of gives you an idea. So in this 35% seawater, obviously I made a very oversimplification there. So we can see in reality, it's a mix of sodium chloride, and then there's also sulfates, magnesium, calcium, potassium. So that's kind of cool. And so you can also measure other concentrations. So you have dissolved CO2. And CO2 dissolves nicely in water since it makes carbonic acid. So that's carbonic acid. And obviously there's other things in there as well. So notice this drops down in the parts per million. So 1 in 1 times 10 to the 6th then. So you can appreciate that. And of course small iron, so random other elements. So lithium, although I'm assuming that's lithium salts. Although not clear, that might actually just be, no, that doesn't make sense. It has to be lithium salts, yeah. You guys know anything about lithium? It's what? Yeah. So it is a good medicine. It is also part of batteries. I was going down the lithium in the water train, but yeah, there's different concentrations of lithium too. So lithium, like she mentioned, is used as a medication for bipolar, but also you can just have naturally occurring high amounts of lithium in the water, and some studies have been done, like whether that population is generally happier or how that influences. So a lot of interesting things in your water. You should always look at your local water report just for fun. And so how they used to quantify this is they used to do this evaporation technique. And if you were bored, we could do this in a lab to simulate it. And it would be very tedious, and we would be just watching water boil all day. And then we'd weigh it at the end. And you'd probably be very bored, and it would be inaccurate. You'd be angry. I should have brought this demo. Maybe okay, I'll try to bring this for Monday, or Tuesday, because we have a little demo like this. But you can have just a salinometer, and so basically what we're getting at is, so let's go with a couple of things. So for instance, pure water does not conduct electricity. And so what I mean by pure water is, and we could test our tap water to see how pure it is, but the thing is, right, your tap water has ions in it, and you want it to have ions. So you don't want to drink pure H2O, so that's something that would be used in like a lab setting. It can be referred to as like distilled water, but there's different purities of it, like millipore water would be even more ions removed. But basically, right, if you just have pure H2O, so literally nothing else in solution, right, water by itself can't conduct electricity. So you have to have those ions to actually physically move the charge along and create your circuit. And so tap water should work, but like I said, hopefully on Tuesday I'll remember to bring this demo when we finish up this chapter. But essentially, the more dissolved substances, you can increase the conductivity, and I'll try to simulate that. So basically we can put some salt into a beaker and then just watch how bright that light bulb is. So the idea being, in a freshwater sample, it would not light up. Maybe it would light up weakly depending on your source. And then salt water should, though, burn pretty brightly. And if you were looking at this more sophisticatedly, you could probably measure the actual current and then get a quantitative measurement. So that's how they do it with there. All right. So that's a good point to end on. So we'll end here, and that'll hopefully remind me to bring our demo so we can watch that light bulb in action. And then we'll finish up the rest of chapter 5. So again, just kind of talking more. I know you've been asking about the cycles and water flow, so again, we'll just look at that more. And then we'll do some review for our test on Thursday. So we'll try to review on Tuesday, get you comfortable, and then ready, so test Thursday. So don't forget.
Chapter review, or will you have a test review up for us?
There is some study guide online already, but I'm gonna try to post more math stuff and like more examples so you feel comfortable. And if nothing else, I'll have something by Tuesday.
So is this first test gonna be like math heavy?
And right, I promise I'm not gonna make it too math heavy, but just, so it shouldn't be too bad.
I've been worried that we haven't been spending enough time on it, and I don't know.
Well,
the material.
that's why, right, office hours, ask questions, make appointments with me, I'm available to help. So that's where, right, you have to get individual help, because everyone's at different levels too. So you just have to let me know what you need.
This is okay, I forgot to put my name on.
Oh,
my
yeah.
stuff.
Yeah, and you can put it there.
I just read it's supposed to be not online paper, is that okay?
Oh,
Is this
it's
okay?
fine, yeah, it
Okay.
doesn't matter.
Do you want this?
Yeah, you could put it there. And then, so are you, in a group with Nicolette?
Pardon?
Are you in a group with Nicolette?
I was the first week, last week I wasn't, but we're closely associated. So,